introduce the speaker. So it's my very good honor to introduce Jichao Fang, who is a PhD candidate at the Northern Illinois University. And he's working on the intersection of machine learning and remote sensing across Mars and Earth. And his research centers on building and evaluating self-supervision vision models, vision foundation models for planetary imagery. He developed a content-based image retrieval system for Mars surface imagery, which is what we'll hear about today. And his ongoing work spans large-scale Mars image annotation for vision language pre-training, benchmark design, and geospatial foundational models. He also has applications of planetary or geofoundational models ranging from crater analysis to the evaluation of alpha Earth foundation embeddings. So today I'll pass it off to Jichao. Go ahead and share your screen and let's hear about his work on using a Mars foundational model for image-based content retrieval.
Thank you all. Uh, Hi everyone. I'm very excited to be here to share my recent work. Most of the content I have talked on the LPSC special session on AI last month. It was an amazing experience, and thank you all for joining me today. I'm a PhD student at Northern Illinois University and will be joining University of Arizona as postdoc later this year. I'm mostly interested in foundation models for Earth and planetary science. So this talk, I'll give a brief introduction on first on a vision foundation model I pre-trained for Mars and the application that I think most beneficial to all planetary scientists. Foundation models, we are now entering the era of foundation models. They are everywhere. We know that Geo AI has been utilizing Geo foundation models on all kinds of tasks and have successful applications. But when I started this work about a year and a half ago, by then there is literally no domain-specific foundation models for the moon or the Mars. So we decided to train our own. So this is our paper about this work, which just got accepted by GGR Machine Learning and Computation. It will, thank you. It will come out in a few days. Welcome to check out. So I briefly introduce this model. This model is basically a vision transformer model, vision transformer based model. For the pre-train strategy, I used the two-stage pre-train. For the first stage, it's a masked autoencoder. It's a pretty common pre-train strategy for all kinds of vision tasks. NASA's PRISV model and the Clay model, most take this strategy because it's very effective and efficient. So for the masked autoencoder or MAE strategy, the idea is that we take the original CTX image as a target, randomly mask out a large fraction of its patches. Here is about 75%, and ask the model to reconstruct what's missing. So by teaching the model to reconstruct the missing patches, the model will learn the underlying structure and the texture of Martian surface instead of just memorizing the pixels. So in the stage two, which is less common in most pre-trained geospatial foundation models, I use the self-distillation contrastive learning strategy, which is adapted from the first version of Dino. Mm, So in Dino model, there are two model, a teacher model and a student model. We give it a CTX image and it randomly crop global views, larger views, and smaller local views. The teacher only sees global views and the student see both global views and local views. The core concept of Dino is that uh, uh, by matching the loss between the teacher and the student, the setup teaches model that different crops of the same thing should map to similar representations. So it encourages more semantic view invariant features. So by doing so, we are not only let model to learn pixel level reconstruction, but also semantic level latent features. A crater is a crater, and a ridge, a valley is a valley. So we tested our model on several benchmark datasets, include Dumas 16 dataset, which is a landform classification dataset. And we also tested on the newly released Mars Bench dataset, which is a suite of dataset designed for Mars missions, including detection, segmentation, and classification. And we can see that not surprisingly, pre-trained model on Mars nearly outperform in every task like crater segmentation, cone detection, frost classification, dust classification, etc. So now we have models, the AI models in planetary science, the foundation models in planetary science are thriving. So it's no longer the case that we don't have foundation models. And NASA and other teams are also actively developing models. But still, sometimes it may seem overwhelming because we now have models to choose from. So what can foundation models do? How to turn them into real world use? Do we need to train them? Do we need to do so-called fine tune? And how to use them effectively? So my question is, I ask one question for all this detection, segmentation, and classification task. Which task type has the broadest audience tackling most painful issue? So basically, I'm asking which task can help planetary geologists and planetary scientists the most without the pain to train to dealing with the models. So my answer is retrieval. We can use retrieval system as a science enabling tool. Because when we are doing mapping, searching, exploring, trying to find regions of interest or similar places, we are doing retrieval tasks like finding books from library. So retrieval in image regime is like search large archive of similar images via image embeddings. So it can be used for localization, analog search, it can answer, I gave three examples, questions. It can answer, first, given an image or a screenshot of a random places, can the retrieval system identify what it is or where it is? The second question is, if I have an interesting place to look up, can the system find all similar looking places on Mars? And the third application is about comparing or ranking two features. For example, given images of two similar looking craters, can the system answer the question, which one is more degraded or which one is more preserved? I'll talk about each example later. So first, what does the similarity of image embeddings look like? So the left image is an RGB composite of first principal component of the embeddings, showing the Jezero crater and the surrounding regions. We can see that visually, different regions appear as different colors. There is distinct difference between the west part and the southeast part of the image in terms of orbital brightness, contrast, and the surface texture. So I basically pass the image to our model and generate embeddings, and those embeddings are like the hyperspectral features. So this false color image is like the false color image of a so-called latent spectral representation. we can further sample a few points uh, to see how other areas similar to sampled region. For example, the higher similarity score. If we click this crater rim and the rim has been highlighted, and as well as other wall-like structures. And if we click the southeast region, the bulk has been colored red. This might help identify structure and geological boundaries in the mapping cases and classification as well. So now I will begin with the three questions, uh, the examples. So first question, it answers, where is this crater? It's a localization and identity search question. So first, to do the experiment, we embedded all craters from Robbins crater database with their canonical views and use them to search index for instance level crater search. So by instance level, I mean we are trying to find if the system can return the exact same crater by giving the query image. It's a non-trivial task because we are not querying image used for database. It's not the whole view, but instead, as shown in first column, they are only partial views and differing lighting, brightness, and contrast. In all three examples, the system successfully returns the correct instance as the top similar image bounded in green here. I think the most interesting example is this one because we are only give it a part of the crater and all these similar craters look identical at first sight and all have a smaller crater to their bottom right. But our system can identify this is in the first result. This is exact the crater we are querying for. The second example is the distribution of the certain landform. So here we query two images, search from our database of entire Mars 30 CTX image. That's over millions of images to search from, and we plot the distribution of top 50 search result. So the first query image is from Serenius Forsey, highlighted in yellow, searching from millions of images for similar looking places. 49 out of 50 most similar results come from the same geological region. Of course, that's Serenius Forsey. It's a fantastic result. The only outlier is here because they do share similar visual appearance. The second query is from a wall segment of Valles Marineris. The result, instead of concentrated in one region, distributed evenly along the valley and most latitudinally on some crater walls. So both examples demonstrate how the foundation model embedding can enable rapid global scale comparative geomorphology without requiring manual mapping or prior knowledge of feature distributions. The third application is about using similarity as a ranking engine instead of traditional classification or detection tasks. So, for example, uh, um, for crater preservation state, normally they are a classification tasks. They are categorized as class 1, class 2, class 3, or class 4. But the changes between them are actually gradual, and they can be hard to have a decisive boundary between each classes. So classifying crater preservation state mostly is a subjective matter. But similarity search, you can actually catch the nuances between these states. And you can query one image, you got a ranking of craters by similarity, which gives you more control than training a classification model. You are not only have simply class one, class two, but you have gradual increase or decrease in the preservation state. And that's the cases for similarity search. You can have the similarity score along different cases. So now there are demo of the website I deployed for Mars scale similarity search. This is the image from Valles Marineris. So we can see it spans across the valley, and and if we click each result, we can see that they look similar. Yeah. And the second case is for, uh, so I want to emphasize that the video has not been sped up. So basically, it's near real-time sub-second performance of searching over 26 million images on a single cloud server. They are all condensed in one region. So basically, we can say, yeah, that's the region the image came from. So some quick technical details about the retrieval system I deployed. We indexed over 26 million images from Murray CTX. That's almost exhaustive, non-overlapping, non-skipping of the whole CTX imagery. Each image is passed to Vision Transformer, the VIT model I trained, and resulting in one pooled 768 dimension vector for primary indexing. Actually, this number is pretty large, and as we can see, learn from alpha Earth embeddings, maybe something like 32 or 64 can be enough, which reduces the storage cost. And we also do two-stage search. Additional 32 tokens are used for second stage re-ranking after shortlisting. It's a Colbert style retrieval, which is pretty common in document retrieval. For the whole system, hosting 26 million images and handling the retrieval, a single self-managed cloud server can handle that elegantly. With only 96 gigabytes RAM, 16 CPU cores, and 1 terabyte storage. No GPU is needed. So of course there are limitations to current system because as we can see that search is scale dependent and scene dependent, and the model sometimes will struggle between similar lighting conditions instead of focus or pay attention to finer granular details. And it's hard to do a object level search right now. That's the problem I want to solve with that crater search example. And right now it's only support image, no other modalities. And I know that everyone wants text to image search. We just type craters, we just type valleys, and we can. But let's leave that to the future development. And for conclusion, foundation model powered image retrieval can serve as a science in enabling capability for Mars surface analysis and beyond. But as we can see, the system is not perfect. Building a robust, scalable system calls for continued engineering development and a collective community effort. I think that's what our talk, seminar, webinar all about. Yeah, we are trying to build a community, and we can together build a very useful system for the planetary scientists and geologists. And the website is findmars.space, and you can try out. It has some examples, and you can also upload your own image to see how it goes. And you're welcome to suggest. And that's all I have. Thank you.